Hi there. Today we're looking at transformers or RNNs, fast autoregressive transformers with linear attention by Angelos Kataropoulos, Aporvias, Nikolaos Papas, and François Fleuret. So this paper on a high level proposes to interpret the attention mechanism in transformers with in terms of a kernel function, and therefore the resulting higher dimensional linear operation can be used to formulate the linear transformer, which is orders of magnitude faster than a classic transformer. They also show that in the case of autoregressive transformers, this makes the transformer essentially equivalent to a special kind of RNN. So yeah, that's what this paper is about, and I think I have some comments to make that I haven't really seen made by others, though I have to admit I also haven't really looked at many comments. So I might just be telling old boring things. As always, if you like content like this, consider sharing it out. Leave a like if you liked it. Leave a comment to let me know what you think. I do read the comments, and they're generally comment section is very, very helpful to me, and also people respond to each other. It's fairly cool to see that the community is usually very helpful to people asking questions. And yeah, just let me know what you think. All right, so what's the problem with transformers? And I've done many videos on transformers, and I keep referring back to them for people who don't know what it is. But there's this original paper called "Attention is All You Need" where I made a video about that. So if you don't know what transformers are, you can go look at that. That should basically cover everything you need to know. But there's many more transformers in the meantime. There's BERT, GPT-2, GPT, whatever the number is after that. Many sequence processing models are now transformers. Many set processing models are now transformers. So this has reached made a very big splash in the community. So essentially, transformers come with this attention mechanism where you have an input set, actually, but let's consider it a sequence. So a sequence of text, maybe, like I have an ice cream cone, something like this, and you want to classify the text, or you want to perform language modeling. So in language modeling, the problem is as follows. I give you this piece of text, and I ask you to predict the next piece of text. This was kind of the first task that these transformers were used on. And this is what is called an autoregressive transformer, because you always have a piece, you predict the next piece, and then I give you that entire piece, and then you predict the next piece yet again, and so on. And this autoregressive property is gonna, come in play in this paper later. But ultimately, what you have in a transformer is called an attention mechanism. So an attention mechanism is the following. Each layer in the transformer you can imagine as having the same number of nodes, kind of the same number of neurons as your sequence is long. Now, from this input sequence, you're going to generate, for each of these tokens, you're going to generate three different things. You're going to generate a key, a query, and a value. So in these you do so usually this doesn't come in form of a letter, right? This comes in form of some kind of embedding vector. And from that, you're going to generate three different things. I should probably use different colors so this is a function. You're going to produce three different things from that. You're going to produce a key, you're going to produce a query, and you're going to produce a value. Now, the key is, you can imagine it being attached to this lower layer right here. So that's the key for this this token right here. That's the key here for that token right here. It's a word piece, right? So the keys again are also just vectors, vector. The query you figuratively attach to the top layer right here. So the queries, they go here for each token, and they are also vectors. And the values will keep out of it for now. So the queries and the keys define basically how you route the information. And you route the information by going over each, you have to imagine each token right here, this have, it needs to aggregate information from all the other tokens, right? So we're going through multiple layers of this, and in each layer, each of these tokens is aggregating information from the other tokens. If we do this in multiple rounds, is eventually, each token is aggregating information. Eventually, each token knows about all the other tokens. But how this information aggregation is done is very important. For example, if the token is a pronoun, it would be very interested in information coming from any sort of named entity in the sentence, because it very much wants to know what it is referring to, right? If you are the pronoun in the sentence, it is very vital that you understand which of these things you refer to. So you'll start aggregating information for that. And then once you know who or what you refer to, then the other parts of the sentence can make use of that information. So they will start requesting information from you. And so layer after layer, each token aggregates information from each other token. So this works by, let's say we're at this token right here. What we're going to do is we're going to form the inner product between that vector and each of these vectors. And then we're going to transfer that into a softmax, which makes this into a, first of all, so we do the query together with all the keys, and then we run it through the exponential function. And after that, we're going to normalize it by the sum of all the exponential functions. That will give us a properly normalized distribution, so a histogram basically of where we are going to get our information from. This is going to be the highest where the inner product right here is the highest. So from this token right here. And this is fairly standard. What I drew by accident is fairly standard, that a token probably wants to know a lot about itself. So you want to carry forward the information that you already have in this particular token. That's why your inner product is going to maybe align a lot with your own key. So the keys and queries are learned. So each token decides what kind of information it wants to advertise to the others, and then also each token decides what kind of information it wants to gather from the others. And the routing then is put through a softmax function, and that gives you this right here. You do this for every single token. So the problem with this is that every single token needs to do the inner product of its query with all the different keys. Then each of that has to go through the softmax, and then the value that's actually aggregated are these values right here. Now the values are simply a transformation of the incoming values. Values are what's really propagated. You can think of it as just like a one-layer neural network. Ultimately, you could also leave away the values. People don't do this. Some people do the same queries and keys, but the values are just a transformation of your input. So the important thing is this right here. This decides how you're going to aggregate the values. All right, so this has a quadratic complexity. So if you have n input tokens, then this entire process will require n squared operations, because you need to form the inner products between each pair of queries and keys, right? And it also is going to require that much memory. And this, we're going to see, this is in large part due to this softmax operation, because we have a softmax, it makes the whole thing nonlinear. And it being nonlinear basically means we'll have to, store everything, keep everything around, and we have to recompute for each query. We're going to see in this paper a formulation where if we make the whole process linear, then will not have to do that. So let's dive into it. So here they go, linear transformers. And they start off with saying each transformer layer is essentially this right here. So this is kind of a higher level view. What we've viewed so far is just this part right here. This is the attention routing mechanism. Each layer is actually wrapped in a residual connection and also a simple element-wise or row-wise feed-forward layer. But these things are usually not that much into consideration. What's really hurting in the transformer, if you go into very long sequences, is this attention routing mechanism. So the attention routing mechanism is as follows. You can see right here, this is the formal expression of what I described right here. Here you have and notice this is an outer product. So if I have n sequence elements, the Q right here are the queries. So this transforms each of the n into a d-dimensional space, right? And also the keys will transform each of these into a d-dimensional space. So this here is going to be a n by n matrix, right? This Q KT is going to be an n by n matrix. This is X, WQ, WK, X, and this transposed right here. Nope, yep, like this. Okay. So this is sort of an outer product, and then we're going to take the row-wise softmax, and that will give us for each row in this matrix. So for each row in this matrix, we're going to have this distribution of how to aggregate information. Each row will give us basically for each of the upper level tokens, for each of the outputs, how we need to aggregate information from the inputs. And the information that we're aggregating are these values right here. Now, they generalize this. First of all, they say we can write it in this form right here. Instead of having a softmax, we can actually think of any kind of similarity function between the queries and the keys. So here you see what we want to do. If we want to calculate output I, here the important thing is there is no longer, this is an entire matrix, and we considered a row-wise softmax. And now we write this out into the individual elements of the output. And we can do so. We can say, okay, how do we obtain one element of the output? We're going to calculate some sort of similarity of that particular query. You see I here, I here. We're going to calculate some sort of similarity between the query of that particular output with all of the keys. So here you can see all of the keys of the input. And we're going to normalize, right? This is the normalization that happens also in the softmax, and that will give us like a histogram of how we aggregate the values right here. So all of this red stuff will give us again some sort of a histogram of how we're going to aggregate information. If you look a bit like this and you know how the softmax is defined, you'll see that if we plug in the exponential function as the similarity function, then you'll get back to the softmax. Okay, they say here equation 3 is equivalent to equation 2 if we substitute the similarity function with the exponential function. Now they go ahead and they go into kernels. So for that, you sort of need to understand what a kernel is. A kernel is a special kind for the purposes that we are looking at here. A kernel is a special kind of a similarity function. It needs to have some properties right here, but essentially they say, well, this kind of looks like a kernel, and we will simply say, okay, here, this similarity, what if we use a kernel here? So a kernel simply is a similarity function of two vectors. If you interpret it like that, it has some more conditions. I know, don't freak on me. But the interesting properties about kernels is that if a similarity function is a kernel, it means that there exists a mapping. And where do we do? So if k between a and b is a kernel, if k is a kernel, that means that there exists a function phi such that the kernel between a and b can be expressed as a linear product between phi of a and phi of b, like transpose. Okay, this is an inner product. So what it means is that this can be like a super nonlinear function, a kernel. For example, it can be, and the example often given in like machine learning classes is maybe something like this. You have one-dimensional data, right? And here is 0, and you have two kinds of data points. You have the x's right here, and you have the circles right here. Now, I cannot classify this data linearly. However, I can transform this into a higher dimensional space. So my function phi of x is going to map to the vector x squared. And that will transform the data into a two-dimensional space, right? And the data will look something like this. So it's going to, the y-axis is going to be the square of the x-axis, okay? And like this. And now I can find a linear classifier, okay? So in this case right here, you can see that in this higher space, things become linear. Things become linearly classifiable. And very similarly, like this is, you can define the similarity between things right here. So the similarity function would be the square function right here. And this would be an example of a quadratic kernel. So this function right here can be very non-linear. I mean, it can be a linear function, but it can be very non-linear, but it is equivalent. It is equivalent. This means it is equivalent to a linear function in a high dimensional space. Now, to figure out what this function phi is the big question, of course. For a couple of kernels, we know the function phi, right? For the quadratic kernel, for example, we just saw that phi maps this to the vector of the coordinate and its quadratic to its square. We know for a couple of other kernels what their associated functions are, but in general, if it's a kernel, then we can just replace it with a linear function. With this thing. And in reverse, we can just say, well, what we could do is we could just simply define a function phi and basically map these a and b into a higher dimensional space where this super duper nonlinear function would just become a linear function. Wouldn't that be much easier? Linear functions are much easier to work with than nonlinear functions. And if we know that as long as we get the correct phi, we do exactly the same thing as the nonlinear function, that would be helpful. So there's an entire literature, an entire like decade of kernelization and kernelize everything, kernelized SVMs to start, but then you can go way further in this. And this is just the beginning, and this is just a very sloppy explanation by me right here. But ultimately, they're saying, hey, instead of doing complicated nonlinear similarity function like the softmax, can't we just project A and B into the higher dimensional space and then just do the linear inner product and do the same thing as the softmax? And the answer is yes and no. We know that for the softmax, the particular phi function that we would need would map to an infinite dimensional space. Usually this is applied in reverse. It's like, oh, here, instead usually in machine learning, they say, we want to do this. We want to map it into a high-dimensional space such as linear, but we can't because these spaces are too high-dimensional, and therefore we find an equivalent kernel function. And it's usually said, well, we've used an RBF kernel that corresponds to an infinite dimensional space and so on. That's pretty cool. Here it's the reverse. Here it's we want the linear function, and the equivalent of the softmax function is an infinite dimensional function, which we can't do, right? We can't feasibly compute an infinite dimensional space explicitly. So it's not possible to just do the equivalent thing than in a transformer. However, you can still do something else. You can still use polynomial kernels. You can still use any kind of kernels that have corresponding functions that map to a finite dimensional space. And that's what this paper does. So here they say if we have such a function that maps these things into a higher dimensional space such that their inner product, such that the similarity function in this higher dimensional space is an inner product, then we can write it as just this inner product right here explicitly. And then because of the associativity, you can see that here is an I and here there's no I, so we can just sort of pull this out of the sum and as well right here. It don't cross this away. These are vectors, right? But you can see, especially here, you can see pretty clear. Why is there a cursor? Stop! You can see that this here, you have to pay attention to the matrix dimension. So if we use like bracket notation, this is like this. Let's go like this, and like this. Okay, so here on the bottom, you see that there is an inner product. So each output will be normalized by this inner product right here. However, the top is going to be a vector. We know that each output is a vector. So the top will aggregate these vectors right here according to this routing. Okay, but if we write it like this, you can see that what we could technically do is we could technically compute this part here once because it doesn't contain any I. So there's no I in that part. So we could just compute it once because we have these two layers of the attention mechanism. And these K and V, they just refer to this lower layer right here. We could just compute that thing on the right once. That's going to give us a matrix, as you can see right here from the dimensions. And then we can simply take the product of that vector right here, of the vector on the left, with the matrix on the right. And we'd be done. It's one operation, right? Instead of for each thing, going and attending to each other and then do the softmax. Without the softmax, we can all do this in a linear fashion. So that makes it a lot easier. In fact, it makes the computation linear so this is now O of n. Okay. Plus, of course, the work that you have to do for mapping this into the higher dimensional space. But this is also not quadratic. This is done to each of these elements individually. Okay, so this is now, as we said, it's pretty easy. You can calculate the matrix on the top. You can actually also calculate this part right here, this vector. You can aggregate over the bottom. And then if you go through the top, it's simply a inner product with the vector of the queries, and you're done. And this is it in fact in matrix form. You can simply write it down as one matrix multiplication. Seems pretty easy. So the computational cost goes way down, and they use the following function right here. Okay, this is their map to the higher dimensional space. So they say, for our experiments that deal with smaller sequences, we employ a feature map that results in a positive similarity function as defined below. So right here, you have to pay attention. You can't just pick any function, but you can pick a lot of different functions. where LU denotes the exponential linear unit activation function. Okay, like this seems fine. They also say in our experimental section, we show that the feature map of equation 7 performs on par with the full transformer while significantly reducing the computational memory requirements. This, it seems like the original transformer, this choice of the softmax function, even though it's powerful and can't be approximated with this trick right here, it was also somewhat arbitrary. I mean, there is a reasoning behind it, but it's also somewhat like meh. And it's entirely possible, right, that that this here is way faster. So I want to jump this causal masking thing for now and look at the results, where you can see they verify the fact that in terms of time, in terms of GPU memory, if they apply their transformer, and here on the x-axis you see sequence length, you can see that this is log plot, right? These are log plots. You can see that the original transformer right here has a way steeper slope than their transformer, which is the black line right here. The blue lines are the reformers, which I've also done a video on reformer. If you want to check that out, that is also a trick that uses locality sensitive hashing to get rid of the quadratic attention mechanism. Now, the locality sensitive hashing also means that you kind of lose some accuracy, so that's the trade-off right here. But you can see that is also linear. Actually, it's n log n, depending on the sequence length, but the log n is negligible. So you see GPU memory and time way down. And in terms of experiments, it does perform on par. It seems like it has different optimization trajectory, but they show that there is this trade-off for the reformer where you lose in accuracy. They do not experience that trade-off in the linear transformer compared to the original transformer in their particular experiments. Now, their experiments sort of show that they are not on par with the original transformer. Like, they are on par in some of the tasks, but also in some of the tasks they are not on par. For example, this speech data set right here, where they do fairly well. They actually beat the BiLSTM baseline and the reformer, but they do not beat the softmax transformer. So it is still the case that the softmax transformer is more powerful than the thing here, and we'll give some intuition very shortly on that. But the linear transformer is way faster. Here it's 3 times faster, and up here it is 300 times faster. And on MNIST, and if you go on C410, it is 4,000 times faster. Simply by a property of the longer your sequences are that you input, the much more matters the fact that the softmax transformer has a quadratic runtime, whereas the linear transformer has a linear runtime. And I was also surprised here to see that the reformer wasn't that much faster. That's probably due to the fact that it already has like a big overhead in these hashing rounds and so on. That probably is hurting it at sort of a constant level. I guess if you were to up the sequence length even more, then the reformer would also improve a lot more over the softmax transformer. Okay, so what's happening here? What's happening with these with this attention, and why is it different? What makes it different from the old attention? Now, I wanna sort of connect this to the kind of olden literature of topic modeling. So, if you think of this transformer again, of this attention mechanism, what you'll have is a dynamic routing of information, right? So from each output token, you get to look at all the input tokens. If we, for example, select this one, you get to look and you get to decide for each one, how do I want to aggregate my information? Okay, and this is what makes this quadratic. From each of the output tokens, you get to look at all of the input tokens and decide how you want to do that. And that can be very non-linear in terms of when we use the softmax and so on. So that's what makes it expensive. What this thing is doing is the following. It takes all the keys right here. So here we have all the keys, and it's going to map them through this phi function, right? Each key is going to map through the phi function, and each query is also going to be mapped through the phi function into these higher dimensional spaces. And then an inner product is performed between the two, and that decides the routing. This is very similar to like topic models, where if you interpret this right here can be a mapping of my dimension of these keys and queries to the topics. So essentially what's happening right here is for each of the input tokens, we have input tokens here, output tokens here, the dimension of this map defines is how many topics there are. So in these topics modeling, you would have things like I have news articles or words, and then I define like a set of topics, and I'm going to assign each word to a topic, and then I'm going to assign each news article to a topic, and so on. And then you kind of do this dimension reduction, but this can be done in many ways. So let's say this is a mapping to 3 dimensions. What this does is essentially this phi function decides how you're going to map each of these inputs into these 3 topics. So you can say, oh, this token goes here and here, this one goes here and a bit here, this one goes here, and so on. So again, this is a mapping into a, well, in this case, a lower dimensional space. And then this function decides how you're going to aggregate these topics across here. And since this is now a linear multiplication between the two things, so these two are going to be your matrices. This here is going to be your phi of k, and this here is going to be your phi of q. So you can see the difference here between the old attention mechanism and the new attention mechanism, right? The old attention mechanism, each token was directly able to look at all the input tokens and decide how to aggregate the information. And here it's sort of, we have this in-between representation in this higher dimensional space. And we can aggregate in we can distribute in a linear fashion, and we can aggregate in a linear fashion in and from this higher dimensional space. That's sort of how I imagine that. Okay, so you get to distribute each token right here into these topics, and then the outputs, they don't see the inputs anymore, right? You see that in the formulation there is a sum over j. So right here there is this sum over j, and that means that the outputs here, they don't see the different inputs as different inputs. They only see the inputs through the map of the phi function. So they can only see the individual dimensions of that phi function. They cannot see the outputs anymore. And therefore, therefore you don't have the dependence on the big quadratic dependence on this n. Okay? However, you do have, of course, now a dependence on the dimension of the intermediate representation, and they say this, right? This is, reasonable. They do derive the gradients here to save even more memory, so you don't have to, let's say, store of all of these activations. That's pretty cool as well, and they implemented in CUDA. There is code available for the linear transformer. All of this pretty cool. Okay, so the last thing they say, they make the connections to RNNs. Now this is a bit detached from the linear transformer, but because they formulated how they do, they can make this connection. So this now is valid for all transformers, what they say right here. But keep in mind, it is valid for the original transformers in practice if you can make this mapping phi to map to infinite dimensions, which you can't. but the analysis is equivalent. So they say, look, if we write the attention mechanism like this, and therefore like this, what we can do is we can define these two quantities, right? S and Z. And this is what we said before. We can actually pre-compute these quantities right here. Okay, so that reduces to this right here. If now we are looking at a autoregressive transformer, and we said before what an autoregressive transformer was. An autoregressive transformer is you have a piece of sequence and you are tasked to predict this next thing right here. Now, usually if you want to train this using an RNN, you have to run your RNN, input this hidden state, and input that, map forward the hidden state. So you have to do all of this forward propagation in order to derive at this output right here, make the output, and then you need to backprop through time right here. So there is no way to, what you would like to do is you would like to say, here I have a sentence, I can actually make like 5 different training examples from that sentence. So the first one is the one you just saw. I just block off the last word. But I can also make that training example right here, right? When I just cut a second to last word and so on. I can actually make all of these different training examples for language modeling from a single sentence. And what I would like to do is I would like to train them all in parallel, right? I load my data point once. I already have it. Why can't I just train everything at the same time? Like predict this from this word. Now predict also this from these 2 words. And the transformers are, very well conditioned. They are very good at this, basically. So what a transformer can do is if you input a sequence like the thing at the bottom, you can calculate the training signal for all of these different things at the same time. And okay, this was maybe a mistake. You can calculate the training signal for all of this at the same time by using what's called causal masking in attention. So if I have my attention mechanism right here, let's consider it again, right? Let's consider these 2 layers. If I have my attention mechanism, what I want to do is I want to constrain each token to only attend to tokens that came before it in the sequence. So for example, this token right here, I'm going to constrain it to only attend to itself and the past, because it will predict the next token in the sequence, and it would be really easy if it could attend to the input of that token, right? It could simply kind of remember what that token is and then aggregate that here and then predict that. So if for each token we restrict the attention to the tokens that came before it, right? Also for this right here, we restrict the attention only to go backwards. Then we can train all of this in parallel. This is called causal masking. It's usually implemented with like a mask that is like an upper diagonal. And it's a bit unclear if you can attend to yourself, because then I guess this will become the output and you can only attend to this. I don't know exactly how it is implemented, but it is usually realized with an upper triangular matrix as a mask, and you apply this mask to each layer. Now they say that this is actually like an RNN, and with their formulation you can make this pretty explicit. Namely, you have these 2 states, S and a Z, and in each sequence element it's actually like an RNN where you update the S and the Z with these quantities right here. And so it's like an RNN where these are the hidden states that you pass forward, right? And then you can formulate any transformer as an RNN that simply updates these 2 states. But you see, you need the explicit mapping of these of this kernel function. You need this explicit mapping in order to be able to do this, because otherwise this is not going to be a linear addition. It is going to be complicated. You can't do it by simply remembering the past state. So you need that formulation in order to be able to express it as an RNN. But their analysis shows that a transformer autoregressive is essentially an RNN, and you can make a connection in that, and you can actually formulate this as an RNN, which means that you can train in the transformer fashion everything at the same time. But what is cool about an RNN? An RNN at inference time, an RNN, once it has produced, this word, it can then, because if you produce autoregressively, you simply say, hey, I have this beginning of my news article, please finish it. So the model must output the next word, and then from that sequence, it must output the next word, and then from that, the next word, and so on. An RNN, because of the nature of simply passing forward hidden states at inference time, can simply, remember what the hidden states were, input those again, input the output here, and go on. So it's pretty fast at inference time, which a transformer isn't. With their formulation now, if they have the explicit function phi, they can use this at inference time to be so much faster. In fact, on their website, which I'll link, of course, in the description, you can play with image generation using one of these transformers in your browser. So you can simply start a transformer run in your browser. That's how easy this becomes. So you can see the linear transformer with causal masking. You'll simply update these states right here and then pass those forward. So easy. And the backward pass, as we said, I don't want to go into the gradient calculation, but they derive the gradient such that you don't have to remember these hidden states, and it becomes, or it is linear or it saves a lot of more memory than before. Okay, note, so this is the last comment from my side. Note that this causal masking transformers, they are a bit of a hack in transformers. And because, so ultimately, let's say I have this sequence right here. This is given, and I want to predict this word right here. Okay, let's make it here. So I need multiple layers for this. So I want to predict that next word, and I have multiple layers, right? So I want to predict this from the outputs right here. Let's say there is an output node right here. I want to predict that particular word. It's true that I should only be able to aggregate information from whatever was, on the back right here. But technically, in a transformer, it would be completely valid to say that this node right here, which is, let's say that's an article, and it followed by a noun, right, would be able to attend to that one, and then that one would be able to attend to that one, the output right here would be able to attend to that one. This would not violate the autoregressive property, right? But you can see that in the intermediate layer, this node right here is attending to a forward node. Now, if you do things like this, you can't do this trick anymore where you train everything at once, because if this connection exists, that also means that if in this other training sample where this is the word to be predicted, then this node could aggregate information from that node and basically cheat. But the technical autoregressive property is not violated by this connection right here. And you only get this RNN formulation if you do not have these connections, right? So this hack to make the autoregressive transformers train in parallel is actually making the transformer formulation much weaker, and therefore that's then equivalent to an RNN, okay? It's not that transformers in general are equivalent to an RNN, or at least this paper doesn't show that. It's just that these hacked transformers are. And I think that's an important distinction to make here, rather than saying transformers are RNNs if we could only approximate the softmax in these infinite dimensions. I don't think that's entirely true, but it is true for the transformers, the autoregressive transformers that we currently train. Now, Why is this connection so powerful? It allows a token to attend to, tokens forward of it. And what does it mean to be able to attend? Like, let's say it's really important that this token right here attends to that token right here. What would you need to do if you couldn't do that? If you, let's say this is a program, right? So this token is the function f, and it needs the input, this argument a, of whatever token comes in front of it. And it needs to do something conditioned on a. So if a is 1, it does something. If a is 2, it does something else, right? If you can't input a, then you can't simply pass on the output value. What you'll have to do is conceptually, basically you'll have to store the entire code of the function into hidden state. If this is an RNN, right, it can't look forward. It needs to store the entire code of this function f. So all it needs to basically build this map. If a is 1, then this. If a is 2, then this. If a is 3, then this. Store that in the hidden state, and then once a comes around in the next time step, this can be resolved. You can see that this is infinitely more complicated than simply looking forward and outputting the value yourself. So that's sort of the difference in power that these two formulations are talking about. Okay, so yeah, 2 parts to this paper. First part, linear transformer through kernels. Second part, if you formulate it like this, it is equivalent. So a autoregressive transformer in this way becomes equivalent to an RNN. And here is some of the output samples. They're pretty good, though. If you look at the more output samples they have here, so here, this is the linear one, and you can see, for example, as already in this very bottom one, this one right here, it's that kind of all the other transformers get the slant to the right, and that the original has, whereas this one is simply straight. I mean, I don't want to dunk on this, like these others make a lot of mistakes right here, but here I also saw, all of them get that this is going to be the number 3, while this one is somehow making this circle in here. So it is not perfect, and even though it's on par where in the tasks they see, you can see right here that especially in this speech recognition, the original transformer right here is significantly outperforming the linear transformer, which is the one in black right here. In fact, in all of the tasks, but ultimately it might not matter because they reach, the same accuracy or whatnot, and the linear transformer is way faster. So I can see that this is going to be a thing that people apply. I guess time will tell. Right, I invite you to read the paper. Tell me what you think. I might be totally wrong here with any of my formulations or my intuition about what this new attention mechanism does. Yeah, please let me know, and I'll see you next time. Bye-bye.